Well, hello, my name is Mike Sinke, and this is Econ 3460 forecasting. Uh, Let me just tell you a little bit about the structure for this class. So all lectures will be available online. Now, I will try to use course time to troubleshoot with R, maybe teach a little bit of programming in class. I'll make that content available online as well, but if you have specific questions, it's often easier to get immediate feedback in the class. So if you're having difficulty solving problems or understanding different concepts in the material, I think it's important to reach out to me online. I also think coming to class could be beneficial, but it is optional due to COVID-19. So all of your homework, quizzes, and midterms will be online. We will be using R and R Studio. So you should have received an email from me about installing them on your computer prior to the start of the semester. And it's important that you install them as soon as possible. Now, R and R Studio are available on the virtual labs, so it is possible for you to use these remotely without installing it yourself. However, I think you'll be better served by taking the time to install it yourself. We will occasionally use Excel in this class, but the bulk of statistical work will be done in R. Let me talk about the grades. We have a point system in this class, kind of like every class that I teach. 10% of your grade is based on weekly reading quizzes. So we have 12 total quizzes. They're worth 5 points each. You keep the best 8 scores. So rather than opening, reopening quizzes, dropping based on whatever comes your way, I think it's just better to build in 4 drops. That means you can fail 3 quizzes and be fine. Now, if you fail 5 quizzes, one of them will count negatively against you. That's just a part of keeping you honest. But the reading quizzes are designed to get you to engage with the textbooks, which are provided for you online. So we have 2 textbooks for this class, which I'll describe later. 15% is for non-R problem sets. So the first non-R problem set has already been posted online. They're worth 15 points each. You keep the best 4 scores. So we have 5 total. We keep the top 4. The goal of the non-R problem set is to get you to learn some of the math associated with cross-sectional regression and forecasting. So that is the objective behind the non-R problem set. Now, the R problem sets, we have a total of 5 as well. Those are worth 20% of your grade. I don't drop any of them. A major component of this class is to learn how to program in R. So we're not going to learn how to program in R if when we encounter a challenge in R, we just don't do it. So I want us to make sure to learn how to use this program. Hence 20% of your grade is learning how to use this program, and an additional 15% of the grade will involve using this program for a small forecasting project. So that project may be cross-sectional, it may be time series. We'll let you develop that as the semester rolls along, but some of your grade will be based on a project that may require you to use either cross-sectional or time series data to either estimate a regression model of interest or to do some forecasting. 20% of your grade is based on midterm 1. Midterm 1, you'll have 3 days to complete it. It's a take-home test. It's worth 80 points, and the same for the final exam. The final exam will be offered prior to finals week. So prior to finals week, you'll have your final exam. The project will be due during finals week. So prior to finals week, you'll have the final exam. During finals week, you'll present your project to me. Let's talk about the expectations for forecasting. So my expectations for this class are that you're going to work hard for this class. I think a lot of classes you're going to take in the next year may be, I don't like to use the phrase watered down, but they may not be at peak difficulty just because of the complications associated with COVID-19 and implementing classes. And I think that tack is understandable. That's a little bit of what I plan to do in stats too. But at the end of the day, you guys are going to graduate into an economy that's as weak as it's been in your lifetime. So having skills associated with programming and learning how to do quantitative work are having those skills is essential, and you need to learn them. Learning them is hard and it takes time, and it's something that's going to require a lot of effort and thought on your part. So I do understand this is daunting, but my goals for you are to program in R. I don't expect anybody to be completely fluent programmers by the time you leave this class, but I expect you to have a loose understanding of how the program works and to be able to write a very simple script that could estimate a model, forecast some data, perhaps clean some data, manipulate data in some meaningful way. I expect you to be able to do those things. I expect you to learn most of the major forecasting methods. So those could be cross-sectional, as in the lens of regression, or they could be time series in the case of time series forecasting. But I want you to learn as many of the time series methods as are reasonable within the course of the semester, and also to have some idea of how to estimate a cross-sectional regression model before those of you who are taking econometrics go on to take econometrics. So it's important that we have these skills for any type of data analysis job that we may take in the real world, and we're going to try to develop them as much as we can in this class. It's going to take time. It's going to take a lot of effort. So I don't want to scare anybody off, but by the same token, I think this is going to be more work than many of you are used to in your classes, and I simply think it's a must. I think we have to do that. So this class is going to be hard to complete if you wait till the night before or 2 days before to start tasks. You're going to have a hard time if you don't engage with the material on almost a daily basis. Now, I do want to point out that I'll give anybody who engages with the material at a cursory level. You try the problem sets as best you can. You try midterm one, you try the final exam, you try the small forecasting project. You put forth a reasonable effort. Maybe you don't get all the questions right, but you try as much as you can. You take the quizzes. I'll give you a C in the class. However, I want us to shoot higher than that. Okay, so there is a textbook for the class. I expect you to read it. This is the latest version of Forecasting Principles and Practice by Rob Heinemann and George Athanasopoulos. Let's just pull it up here. You can see the book is right here. Okay, so this is an extensive book about how to forecast. Rob Heinemann is the editor of the International Journal of Forecasting. So he is arguably the most credible teacher of forecasting available, and this book is amazing. It's as it says, it's a comprehensive introduction to latest forecasting methods using R. Couldn't recommend it more. I think this is just a wealth of knowledge, and it's written at a level you can understand. So this is an awesome book. I even have a picture of the book there. See, there's a second book for this class. This is kind of falls in the span of between lecture notes and a fully completed textbook, but it's Bruce Hanson's econometrics book, and I don't expect us to read much, if any, of this book, but what I do think Bruce or Dr. Hanson does a really good job of is explaining some of the details of regression in a non-technical way. So I want us to read those parts. Almost the rest of the book is too technical for us to understand. However, from the parts that are assigned reading, I think we can get a lot out of it, and I expect us to look at those parts with great interest. I make the slides for this class myself, but I base them on both the forecasting textbook and my own knowledge of cross-sectional regression, as well as complements from the Hanson econometrics book when I can. So most of the regression notes will be from me. Most of the forecasting slides will be based off of what I think is important out of the Heinemann Athanasopoulos book. And so we are going to cover some basics to kind of bridge the gap to regression. So I think that in statistics, we spend a lot of time dealing with samples. And in this class, if we're thinking conceptually about what regression is doing, we have to be a little bit more deliberate about at least giving a cursory amount of attention to the population, sort of how do population variables behave, looking at the first few moments of those population variables. So we're going to do that. Okay, so a couple of comments about forecasting. Forecasting is one of our upper division electives in economics, but I think broadly speaking, it is not economics per se. And what I mean by that is I think of forecasting more as a mix of statistical applications, which don't necessarily correlate with a person responding to an incentive, which is what we think economics studies. So often forecasting is offered in either a finance or management department rather than economics because the applications of forecasting are statistics to business problems. So economics does have quite a few tools, and the nice thing about offering this in an economics department is that we can spend a little bit more time on cross-sectional regression, which I think is arguably a more important type of forecasting tool now than maybe it would have been 15 years ago when it was appreciably more tedious to put together a data set. You often had to do that sort of thing by hand. Now the data are collected, processed through a database, and you can get a usable data set fairly quickly. So you have some more tools in the toolbox to use to solve a business problem. And then economics does have a lot more to say because regression is a key component of econometrics. Okay, so to start with what this class is about, we're going to look at three different data structures in this class. The first is what is called cross-sectional data. And I want you to think of cross-sectional data as being a snapshot of different observations, but at one particular point in time. So, if I go online to ESPN.com and I pull it up and I look at the Braves statistics for this season. So I go to stats here and I look at the Braves statistics. So I go to team statistics here. Okay. You can have a look at the Braves statistics here. These are the player statistics for the Braves. You see Swanson, Ozuna, Freeman, Acuna, Ozzy Albies, etc. They're all listed here. And this is as of Friday. This is how they've performed up to this point in the season. So you see that the number of games played, the number of at-bats, runs, hits, doubles, home runs, triples, RBI, total bases, walks, strikeouts, stolen bases, the batting average, the on-base percentage, the slugging percentage, the on-base plus slugging percentage, and the wins above replacement. You can see that all of those vary among players. But those are taken as of today. Now, if I compiled this data every single day, okay, and had Dansby Swanson's at-bats on Thursday and then added the at-bats on Friday and had a new variable for that, etc., I would have a panel of data. I would observe multiple Braves at multiple periods of time, and I could potentially observe all of this data. So if you think of like a longitudinal survey, something where subjects are asked repeatedly, maybe year after year, that is a panel of data. But a cross-section is just at one point in time. So what I pulled up here, this is a data set, it's cross-sectional. It's just for Friday, August 14th. Now a time series, let's say I'm looking at US GDP. Okay, I can measure that quarterly. I can measure it from every period since World War II, quarterly. That is the same time series. Okay, it is one data point. It's the United States. I can observe it at many different periods of time. Quarterly, that is a time series. So I see it for quarter 1 of 2020 and quarter 4 of 2019 and quarter 3 of 2019, etc. And I think of getting a new piece of information every time I arrive at a new location on a timeline. So in this class, the bulk of the data sets that we work with are going to fall into the first two categories. However, we may consider using some panel data if time permits. So, if things go super, super well in this class, maybe we can look at panel data. Otherwise, we're going to be spending a lot of time with cross-sectional and time series, which is great. So let me give you some common examples of cross-sectional data. One is customer data pulled from a database. So when you purchase an item from, let's say, a clothing retailer, you fill out some information. You fill out your address. They know which items you purchased. They know how much you spent. They may know the website that linked you to the purchase page. So if you went to their purchase page from Twitter, they may know about that. They may know previous purchases. They may not. So I could think of that data as being cross-sectional. An inventory list. So if you're a business, say Tractor Supply Company, you sell a myriad of different items, and at any particular time, you know what items you have in stock and what items you don't based on the database that you have. And at that particular point in time, that is a cross-section. If we observe all county level unemployment for a month, that's cross-section. The long-form census, which you have to fill out every 10 years, which I filled out recently, that is a cross-section. Surveys that you do for your marketing class. So you may ask people a number of invasive questions about income level, race, demographic information, family structure, gender, sexual orientation, things of this nature. You collect it all along with the questions that you may be actually interested in from the survey. So how likely are you to buy this product, use this service, etc. That's cross-section. So we may observe many, many different things for a particular subject, but we just observe those things at one point in time. And so I think a takeaway point from this is that most, if not all, statistical analysis that we do in both Econ 3402 and in Econ 3406 is cross-sectional, even if the data are collected over time. So you could do something like measure my weight at different months of the year, and we could have a hypothesis about what the average weight that I have is, and when I do the data analysis, take the standard deviation and the mean for a test statistic, I have implicitly treated it as a cross-sectional data set, even though I measured the same variable at different points in time. So that's a time series. And there's correlation between the values in the time series. And we sort of sweep it all under the rug and we say, well, it's cross-section. Okay, so if I'm doing a one sample mean hypothesis test, which is something that's routinely done in Stats 1 and Stats 2, I could actually either have cross-sectional or time series data, but I often just treat it as cross-sectional. And we do this with two samples. We do this with the chi-square. We do this with proportions in ANOVA, and we certainly do this with regression. And so in this class, we'll be estimating a lot of cross-sectional regression, but my hope is that sort of toward the end of the class, we can actually work on maybe estimating a time series regression. So we can do some autoregressive models where we no longer ignore any instances of time. And the ignoring of instances of time is a disadvantage because it ignores correlation between time periods. So our estimates for the slope of a regression are often wrong. the advantage of treating things as a cross-section is that it's easy to think about. So if I just ignore the structure of the data, I can do a lot of statistical analysis pretty simply. Okay, so today we're going to start by expanding some Stats 1, Stats 2 methods of analysis. We'll look at expected value, we'll look at variance, and then later on we're going to look at linear regression, but we're going to focus on expected value and variance for right now. I want to first start by thinking of what is a sample compared to the population. So when you do statistical analysis, the whole point is that I don't know a population parameter of interest. Rather, what I do is I sample. And my hope is that via my sampling procedure, the link between the sample and the population is strong enough that I can conduct inference about the population from the information that I learn in the sample. And to the extent that I can do that, I'm learning about the population. So most data that we observe, however, is observational. So I collect the data from the world around me, and then I just relate those data to each other. And data are often characterized as variables. So variables, I have one specific measurement that differs among observations. When we do this statistical analysis, we're doing it on observational data and we're relating variables to each other. And so we're often trying to figure out if the value of a variable is consistent with what we believed or how these variables move together. And I think it's worth taking a step back and just examining the mathematical properties of, hey, look, if we knew all the possible outcomes, if we knew what the population was like, how do we find the center of a population? How do we find the variance of a population if we know every possible property associated with the population? So what we do is what we've done in Stats 1 and Stats 2 is we've said, look, here is a sample. It represents the population. We're going to do some analysis on it. We haven't spent a lot of time in those classes saying, hey, here are the properties of the population. How are the outcomes dispersed? How do variables move together if they depend on each other? What should I expect to see for a value of a variable? How are probabilities assigned to that variable? When you know with the population, you actually know all the probabilities, and yet we have not spent a lot of time on that. So we talked about how the sample, that we've conjectured that whatever sample we have is indeed representative of the population, which may or may not be true. And we go back to this point here where there actually is kind of a tenuous assumption that the sample is always strongly representative of the population that you're claiming it is. But we haven't even analyzed, okay, well, if we knew how the population's outcomes and probabilities were dispersed, what should we expect? How do we look at the dispersion of those outcomes? So we've done some estimates from a sample to learn about the population, but we don't necessarily have the greatest idea of how the population behaves. And so that is the first order of business in forecasting, is just to establish some simple properties about how population random variables